Go. All right, everyone. Good morning, and thank you so much for joining us for another session in the AIA California Monterey Design Conference University Series. My name is Hillary Kreck, and I am the Director of Programs at AIA California, and I will be your moderator for this introductory part of today's segment. This morning's session is brought to you by our friends at Pacific Coast Building Products in partnership with Interstate Brick, both legacy partners of the 2021 Monterey Design Conference. It's not too late to join us for our first MDC on the road, coming to you wherever you are. The virtual format is our way of inviting you to see what makes the Monterey Design Conference the Architects Retreat and why we have so many loyal attendees. Our headliner speakers this year will join us from Portugal, Japan, England, Boston, and of course, California. Clear your calendar next Thursday and Friday, October 21st and 22nd, to carve out some time to focus on these amazing architects and how their work is shaping the world. More details on our amazing lineup of speakers and registration are available online at montereydesignconference.org. A few quick housekeeping reminders before we get started for today's presentation. Please use the Q&A function to ask any questions for today's presenters. You can also like a question to move it to the top of the queue. And today's session qualifies for one AIA learning unit for those watching live. AIA California staff will report your attendance for you. The session is also being recorded and will be posted on the AIA California website shortly after today's session. So on to today's session. This course is intended to help designers understand the resiliency is a human characteristic related to the ability to return to some semblance of normalcy after a stressing event, and that resiliency can be enhanced by durable infrastructure. This course will teach what characteristics make reinforced hollow clay masonry, RHCM, durable due to the materials and unique manufacturing processes. The course will show examples of testing of the RHCM, proving its durability, and show durable facilities constructed with RHCM. I would like to quickly introduce today's presenter before passing the program over to him. Stephen Judd is the Technical Director of Interstate Brick, West Jordan, Utah, and HC Muddix, Sacramento, California, and is in charge of assisting sales efforts via technical support, regularly works with designers and engineers to provide technical information with regard to fired clay masonry, and gives various presentations on the technical aspects of clay masonry design and detailing. Mr. Judd is involved with developing and updating quality control and quality assurance documentation and is intimately involved with the day-to-day QA, QC production processes. Mr. Judd has over 40 years of experience as a structural design engineer licensed in Utah and California, and has over 35 years designing facade systems. Take it away, Stephen.
Thank you, Hillary. Good morning, everyone. I'm pleased to be here to provide this presentation to you, and along with me, who you probably aren't seeing, are two other members of our organization, Don Strange, who's the National Distribution Manager, and Shannon Perry, who is the Midwest Regional Manager. And they will be monitoring the chat and QA boxes, and will be answering questions as appropriate or interjecting those questions to me as we go along. And with that, let's get this rolling. So again, the presentation is talking about resiliency and the role of reinforced hollow clay masonry. So we're going to talk about resiliency and stressors, the relationship between resiliency and durability. Those can be defined various different ways. We'll give you the definitions that we'll be using today shortly. A little bit about the history of reinforced hollow clay masonry, the manufacture and properties which are key to the durability of this particular material, and then some use capabilities and examples of buildings that have used this particular product. So for this presentation, we're going to consider resiliency a human characteristic. Different people will define it different ways, but from our standpoint and for this presentation, we're going to treat it as a physiological issue, not a materiological, which is not a real word, issue. So it has to do with how people react to stressors. So it's defined, resiliency can be defined as the ability to recover, hopefully quickly, from disruptive change or misfortune without being overwhelmed or acting in dysfunctional or harmful ways. This is a definition provided from the resiliencycenter.com. And so we talk about disruptive change and misfortune, and another word for those are stressors. So what are the stressors that impact our lives or people's lives? So here's the ravages of a tornado. Those people who used to have homes are going to be considered fairly highly stressed and very anxious because they have nowhere to return to for their home or whatever was in those homes. Here's a community that was ravaged by a wildfire. Again, here's an example of a highly stressing event that impacts people's lives. All these homes have been burned to the ground and everything in them. Some additional stressors. If you happen to live near a river, you could expect it to flood at some time or another. For those of you in the Western US and certain areas of the Eastern and Midwest, if you live at or near a active fault zone, you should expect to experience an earthquake at some time or another. And if you live along a coastal area or a seaboard, although not in California or the West Coast, you see many hurricanes, but you can have tsunamis and storm surges that can also do some significant amount of damage. Those are all stressors that are going to impact you. And if it's a prolonged disruption, you may deplete your assets. If you got to go pay to live somewhere because your home is gone, that's a stressing event. And those stresses can affect your physical health and your may cause illness, for instance, because your body is under such high degree of stress, and it can cause mental changes or mental illness. And if it's prolonged enough, you have societal boundaries erode. You have people that are so needful for something, their normal pleasant attitude changes to disruption and maybe stealing and other worse things as a response to these stressors. So how can the built environment enhance resiliency or your ability to bounce back from a stressing event? So you have personal resiliency and you have community or neighborhood type resiliency. So in those photos earlier, you saw the whole neighborhood is wiped out. Obviously, that's a personal and a community issue, but they're related to the durability of the infrastructure. So if your home is built in a manner that resists these exterior or external influences and isn't wiped out or isn't destroyed, that obviously increases your personal resiliency. Same for gas stations or grocery stores. If you need food and the grocery store is intact and functioning, that increases your personal resiliency. Hospitals, fire stations, police stations, those are all considered essential facilities and generally are designed to a higher standard so that they can more readily be available. But one of the key things we're going to talk about today is it is possible to build durable buildings that can resist these stressors through their strength, their toughness, and their durability. So we'll reflect back to a childhood story that most of you probably heard at one time or another about the three little pigs. So we have a house of straw, a house of wood, and a house of brick. And along comes a stressor, the big bad wolf, who huffs and puffs, and what you end up with is a pile of straw, a pile of wood, and an intact house of brick. So what we learned from that is brick is a durable material. Here's an example of a durable home that went through reasonably unscathed through a high wind event that destroyed all of the trees around it. Here's another example of a durable building. All of the other houses in this neighborhood burned to the ground, except this one, which was not built of combustible materials. It can be done. The people who live there obviously are undergoing a lot less stress and have much higher resiliency than all of their neighbors. As durability of the built environment increases, personal and community resiliency increases. So durability goes up, resiliency goes up. Those are linearly related. Now, as durability of the built environment increases, the recovery time and stress levels decrease. So these are inversely related items. So you can see as durability is applied to infrastructure, making it more resistant to these stressors, the better off individuals and communities and whole geographic areas are better. The durability of the reinforced hollow clay masonry, we're going to talk a little bit about the history of hollow clay masonry, how long has it been around, how has it morphed over the years, some of the manufacture and properties, different shapes of hollow clay masonry, the capabilities and durability through some testing examples, and then some pictures of actual buildings and facilities that exist currently. And so back in the day, the Palace Hotel in San Francisco was built in 1875. It was a multi-wide brick building that was basically encapsulated by steel strapping, which they called sort of like a steel basket around the building. So they knew the need for reinforcing. It was applied externally in this case. And this building did in fact withstand the 1906 earthquake. Unfortunately, it did not withstand the ensuing devastating fires that engulfed the whole city. So it was damaged beyond repair and torn down, but not as a result of the earthquake, but as a result of the interior part of the building catching fire. And from that, a multi-wide masonry, the next iteration became interior-wise replaced with basically reinforced concrete. So you've got an exterior wide, an interior wide, and the middle space occupying the reinforcing. So it's sort of like left in place forming out of masonry, with the interior part having properties very similar to reinforced concrete. Then in the 1950s and beyond, this concept morphed to a little simpler construction technique where the exterior and the interior widths of masonry became the outside face and inside face shells joined together by intermediate webs with large openings that allow for reinforcing and grout, very much or very similar to CMU. So this is sort of the redheaded stepchild or brother of the CMU world. And here's what one particular manufacturer's products look like. It's actually 3 cells, and the extra web is there to help stiffen the face. Talk a little bit about the manufacturer of the product and how that relates to its toughness and durability. So every manufacturer, which there are many around the US, has to have raw material. Generally, it doesn't pay to truck it anywhere. So out of the dozens and dozens and dozens of brick manufacturing facilities, only a few of which make hollow clay units, there's hundreds and hundreds of mines or quarries to provide the raw material. It's excavated out of the ground. Some is stockpiled at this quarry site or at the mine site. And then at the end of the day, when the material is depleted, then these areas are reclaimed. In one instance, the reclamation process is using these large pits as a community landfill, and then the reclamation process is transferred over to that entity. And then some of the material is stockpiled at the site of the manufacturing facility. Generally, depending on where it is in the US, in some of the northern and climes that are affected by winter weather, there's several, maybe up to 6 months worth of material stockpiled on site because some of the mines have limited access and maybe zero access during some of the winter months. And from there, it's crushed in a crusher and then ground through a grinder. This is a grinder that gets the particles down to a size that can be used in the extrusion process, which is here we show. It's sort of like the little Play-Doh machine some of you may have had at a point in your life, where the material is squished through a particular die to a particular profile, and then it runs down a conveyor belt generally and is cut by a guillotine cutter into maybe 6 to 10 foot long slugs. From there, the slugs are transported via conveyor to a cutter to produce the right cut height size. Here it's being lifted up through a series of high strength wires to cut them to the size desired. From here, the material is transported by robot over to a QA/QC station where they're inspected for squareness and straightness and flatness. And then from there, they go on to a station where the robots pick them up and load them onto drying racks. Not all manufacturers necessarily have a drying process. Some do, some don't. The drying process is a way to reduce the amount of cracks and things that occur in the firing process, because you want the material as dry as possible before it enters the kiln. The photo in the lower right-hand portion of the slide shows a series of drying racks that are loaded with green product going into the dryer. After the dryer, they're loaded on kiln cars and they get ready to go into the firing kiln. Generally these days, most manufacturers use a linear kiln. Some manufacturers have kilns that are in the neighborhood of 550 feet long that takes maybe 3 to 4 days to go through the firing process. So it's not as quick as CMU, which can be produced between 18 and 24 hours. You can get a huge quantity of CMU produced because it's basically held in the mold, autoclaved. However, brick has to be very carefully fired, which we'll talk about in just a moment. And then the cars go into the kiln, they run through the kiln, which is where the magic happens. And we'll talk really briefly about how that magic occurs in this little diagram called a dilutometry analysis, which is basically a way to measure the volume of the brick as it changes through the firing process. So the horizontal graph are the temperature zones in Fahrenheit in the kiln. And so we're going to talk about this one called the number 80 mix, which is the blue line. So it starts at its green size, so 0 change of volume. As the temperature heats up very slowly, it's continued to dry until all of the moisture is driven out of the product at roughly 1100 degrees. And then it continues to be fired. And you'll notice that it's actually now starting to condense because you're burning off all of the organic materials that might be in the raw material, the clay and the shales that are used to produce brick. And then there's a densification process as it continues to heat from 1600 degrees to somewhere near 2000 degrees. The material actually densifies. The pore structure reduces. The material becomes very amorphous, meaning it's almost fluid. If you burn it too hot, it will actually melt and become sort of like lava rock. And this is the process where the brick material actually increases the strength and reduces the permeability. And those are 2 key factors for providing a durable product. You want it to have high strength and low permeability, so it doesn't absorb much moisture. And it's rated by ASTM. Most manufacturers try and produce product that is rated as a severe weather product, which means it can be used anywhere in the United States or anywhere that has severe weather criteria. And again, if it's fired too hot, you reach the vitrification temperature, which means that's when it all melts into a big blob on the kiln car, which you try and avoid. And then you go through the cooling process. And at the end of the day, once it's cooled back to a temperature that you can handle, you measure the new volume of the material. And in this particular case, the 80 mix has a shrinkage of a little over 1.5%. In comparison to the other mix, the brownish orange line, the 70 mix, only has about 0.5% of shrinkage. So this process is really what produces the material that is highly durable and it has lots of toughness and lots of strength. And in comparison, over the years, CMU strength has modified, has gotten increased. The standard used to be 1,500 PSI. These days it's 2,000 PSI, which gives you a design strength of the wall of an assembly of those units of 2,000 PSI. High strength CMU might be 3,250 PSI, maybe up as high as 4,500 PSI. And you get consequentially, you get a slightly higher design strength of the wall assembly. It's not a linear ratio. The higher the unit strength, it does not equate to the same degree of strength in your design equations. So another popular material is tilt-up concrete panels. Those generally run between 3,000 and 5,000 PSI, which gives you 3,000 to 5,000 PSI for your design strength. Now along comes our wonderful material of structural clay brick or hollow clay masonry. Think of where this might fall in this strength curve for a second. And again, this depends on the raw material that the manufacturer has available. And in most cases, you're talking 3 to 4 and maybe 5 times the unit strength of CMU material. So that's an indication of where you get some of this durability. And that translates to a design strength for the wall of 3,500 to 4,000 PSI, which is generally 1.5 to 2 times what you might be able to use for CMU design. And again, each finished product is unique to each manufacturer because of the raw material that they use or have available at their site. So just because one manufacturer might be able to produce 18,000 or 20,000 PSI units, that doesn't mean every manufacturer can do that. So it's important to know the constraints of the material based on the manufacturing facility and the location where that is. And we'll briefly go into the Masonry Society code, which is adopted by the IBC. And this particular table is for the strength design of the wall based on the unit strength of the material. You enter the table and you pick your mortar, which is usually either type M or S, generally type S for most structural applications. You read down to whatever the unit strength is. In this case, we'll go down to the bottom of the pile, 11,500 PSI, which is sort of an intermediate strength. There can be units that are a lot stronger than that. Read over to the left and you can see in this particular case, the strength design for the wall would be 4,000 PSI. So a significantly robust material. And you can also derive a different design strength of the wall going through a testing process, which most of you probably aren't interested in at the moment. And so here's a little graph showing capability or capacity of various wall systems, assuming 20 pounds per square foot of wind pressure and 1,500 pounds per linear foot of roof load along the top of a tall, slender wall. And we're going to be sort of comparing CMU at 2,000 PSI and reinforced hollow clay masonry at 4,000 PSI. And you can see at any given place, you generally have more capacity available in the brick material or the clay material than in the concrete material. So if you pick a gymnasium, for instance, at 32 feet, you may have to use a 12-inch CMU wall or maybe a 10-inch CMU wall. Here you could also use a 10-inch reinforced hollow clay masonry wall, or you might be able to use an 8-inch hollow clay masonry wall. Now, if you have a series of these walls and you can gain 2 inches per wall, you can create more interior space that's usable. And even for like apartment buildings, if you're used to needing 8-inch CMU, you might be able to use 6-inch hollow clay masonry and gain some interior space, which means higher rental rates and higher lease rates because you've got more usable space. And one of the issues when you're comparing concrete versus clay, concrete shrinks. In order to make concrete, you have to have more moisture than is needed to hydrate the cement particles and bind the product together, so that excess moisture evaporates eventually and the product shrinks. Clay, on the other hand, as soon as it comes out of the kiln, it's as small as it will ever be. Clay has an affinity for moisture, so it tends to expand over time. And so you get CMU going at -6 times 10 to the -4th versus +3 times 10 to the -4th. So CMU has 2.2 times more irreversible volumetric change than masonry. So masonry is a more stable and more consistent material. So here's a masonry wall. Over time, it would tend to expand or grow and tighten up as time goes by and the material absorbs moisture from the atmosphere, whereas concrete tends to shrink and pull apart and crack, which is detrimental for moisture infiltration into walls, especially in single wide masonry construction. Here's some typical profiles of one manufacturer, ranging from, over on the left, a typical modular brick with slightly larger core holes to allow for reinforcing and grout. 12-inch wide units, 16-inch wide units. Typically, they're 4 inches nominally high, although you can get a 8-inch high unit, which is not uncommon, from 4 inches for a wall depth up to 10 inches. And then over on the right, you see a particular manufacturer has a specialty product that can be used to produce a reinforced hollow clay masonry wall that mimics the look of a modular brick installation. And we'll show you some examples of that here in a second. Here's a nice axonometric view showing the different heights, lengths, and depths of material for a particular manufacturer. And these are categorized under ASTM C652 or Canadian Standard A82. Satisfies both of those. Some custom shapes. If masonry is based on an 8-inch module, so if you're building a 6-inch thick wall, you have to have a special corner unit, or you have to do lots of cutting to make up that extra 2 inches at each of the corners. So here you have a special corner unit that has an 8-inch return face, so everything stays on bond for a typical running bond application. 8-inch obviously works all by itself. 10-inch wall, you also may have to have a special starter unit at the corner to again get the 8-inch return face to stay on bond for the 10-inch unit. Other special shapes, you can have a closed bottom lintel member that can be up to 16 inches tall and up to 8 inches long. And then typical bond beam units are a typical unit that is saw cut through the webs. The mason then knocks those little teeth out, lays in the rebar, and then grouts those units full for their bond beams. Some manufacturers can do specialty shapes. Here you see an offset face with a slot. Sometimes the slot's required, sometimes not. You can get circular shapes to build reinforced circular columns. And you can have just a flat face with multiple slots. This is to mimic a sailor course on a particular job that is out of reinforced hollow clay masonry. You can get different textures on different areas of the unit as well. And some manufacturers can also do some coatings to help broaden the color spectrum that's available. So let's talk about some stressors. So this product can be used to resist fire, tornadoes, hurricanes, earthquakes, bomb blast, and ballistics. We'll talk a little bit about each of those. So here's a big oops. They were renovating the inside of this particular building, which was a tabernacle building, and caught fire. A couple days later, after snow, that's what it looked like. You will notice that all of the exterior masonry walls are still intact, maybe damaged a little bit with soot. And the steel roof construction warped, fell down, and all the intermediate floor burned. And you have a pile of basically rubble on the inside of the building. So they wanted to save the building, so they saved all the facade, put it on shores, dug out the ground underneath it, and built a 2-story parking garage underneath the building, put a new lid on it, and repurposed this for another purpose, using the original exterior facade of the building. If a UL rating is required by some jurisdictions, some manufacturers will need to test the product to satisfy the UL criteria. For a 4-hour rating, you build a wall, you subject one side to 2000 Fahrenheit firebox chamber and put thermocouples on the opposite side. You manage those. And the key is that any single thermocouple has to remain less than 350 degrees, and the average of all of them has to remain less than 250 degrees for the duration of the test. And at the end of the test, this particular wall lasted more than 4 hours. So you round down to the 4-hour rating, and then you slide it off the firebox and you spray it with 45 PSI water for 5 minutes to sort of mimic the condition that a firefighter might have. So you don't want the wall to explode when it's hit with this cold water that the wall has just been subjected to 2000 degrees. If you pass the test, then you can carry a Underwriters Laboratory certification for that product. If you go into the IBC, it has a table of equivalent solid thicknesses that can be used to derive different fire resistive ratings. So a hollow clay masonry wall filled with non-combustible material, sand, gravel, vermiculite, perlite, something like that. You can get a 1-hour rating out of a 4-inch wall, a 3-hour rating out of a 6-inch wall, and a 4-hour rating out of an 8-inch wall. And those come out of the table in the IBC. Like I said, if it's important to have for a particular manufacturer, a particular client, if they want a UL rating, at least one manufacturer has the ability to provide that for a 4-hour rated wall. Brick doesn't burn. It doesn't contribute to smoke or create toxic fumes. Painted masonry does. You can create a 4-hour construction wall at a 0 lot line by building it from the inside, which we'll talk a little bit more about that in a few slides. If you use these as devising walls in an apartment construction, you can separate each unit into its own little fire zone. And there's been a recent study done by the NFPA that said out of the active suppression systems, they generally worked only about 88% of the time to impact the fire. This is for commercial buildings. Passive systems work 100% of the time. So consider you go to the car dealer, you buy a car, and the guy says, well, when you use the brakes, they're only going to work about 88% of the time, so good luck. Whereas a passive system that utilizes non-combustible materials works 100% of the time. Storm durability. There's earthquakes and tornadoes that come along in various parts of the United States. Everywhere east of the Rockies, in the next version of the IBC, will be required to consider tornado wind speeds as part of the design criteria. Not too many tornadoes out west, although we have had one in Salt Lake City in the last 15 years. The red zone has a 250 mile-an-hour wind speed, design wind speed. Orange zone, which includes most of the Gulf Coast, is a 200 mile-an-hour wind zone for hurricanes. And then the little dotted areas are areas that are basically considered hurricane zones. And for storm shelters, they have to be able to resist impact from projectiles. So for a hurricane at 200 miles an hour, you have to shoot a projectile at the wall at 90 miles an hour. For tornadoes, for design wind speeds of 250 miles an hour, you have to shoot a projectile at the wall at 100 miles per hour. So here's a little video that will show some of this. This will be showing some vinyl siding walls, some brick veneer walls, and reinforced hollow clay masonry walls. And again, this is for a tornado, so it's 100 mile an hour projectiles, 3 shots per wall. If any of those penetrate, then it's a fail. There's a shot of the projectile. The previous view was the cannon. And here's a couple examples of the vinyl wall. No big surprise that the projectile passes through a vinyl siding building without too much trouble. Here, interestingly enough, for a brick veneer, you can see that the projectile goes through the brick veneer most of the time, more than required to pass. So those also failed. And here's an example of some shots for a 6-inch reinforced hollow clay masonry wall. You can see the test frame displaces when it gets hit with this projectile, but the brick is basically left undamaged. There might be small particles of wood that are embedded in some of the pore structure of the brick, but there's no chips, no cracks. Very durable product, great material for storm shelters. So that's the 6-inch, and not surprisingly, when you test the 8-inch, which is an even more robust wall, it also passes the projectile test. Here's an example of a storm shelter in the community. Very attractive looking thing to have next door to your house versus a storm shelter that looks like this. This particular storm shelter is a CMU primary structure faced with brick veneer. FEMA will not fund any portion of the non-structural portion of this building. So the hip roof is all paid for by the local community or jurisdiction, as well as the veneer facing the CMU. However, if this was built with this particular product we talked about earlier that mimics the look of a modular brick installation, but it's a reinforced masonry product, then FEMA covers 75% of the cost of that material. You get the same look at the end of the day, but you get a higher participation of the total cost of the facility by picking this particular material. So it's a great use for that in residential communities as well as other communities. And there's what the particular product looked like. So it might have a slot on both sides. In this case, this is just slotted on the outside face. Here's a reinforced masonry wall storm shelter that's used for the community. It's also associated with a high school and is used as a gymnasium, all built with that particular product. Here's a convenience store that is built with reinforced hollow clay masonry. And there are signs at these facilities for this particular ownership that rate this as a safe place because these are qualified storm shelters, which is nice to have available in a community. And all the exterior walls are single wide reinforced hollow clay masonry. And you can have, it also is a gas station. You can have reinforced masonry columns, trash enclosures that match the building. They're all single wide reinforced masonry. Can be designed for extreme winds. It's obviously shown to resist projectiles, and it has been used on many facilities. Let's talk about blast durability. I think this is a Hollywood set. You can see those vehicles are being held in place, but it's still a pretty cool photo. And so the two parameters for blast design, it's equivalent pounds of TNT in the standoff distance, and it's not uncommon for the peak incident pressure to be in excess of 100 PSI. Now, in real terms, a design wind, which is fairly common in the IBC of 120 miles per hour, translates to a wall pressure of 36 PSF, which is about a quarter of a PSI. So you compare that to the blast pressure, and you can see that blast pressures are in excess of 400 times the design pressure for wind. So it's a very significant impact. Here's a court building in this happens to be in Tennessee that was designed for the blast criteria required by FEMA. And for post and beam construction, you have a blast. You can have a significant portion of the building collapse, which is happened here. If you remember back at the federal building in Oklahoma City, this was the case that happened there. In contrast, if you have a reinforced masonry wall, you have a blast, you might get a very localized failure of a portion of the wall, but due to the arching action of masonry in general, and especially reinforced masonry, a larger portion of this particular wall is left intact and able to carry the loads for the building. So it's unlikely to have progressive collapse using that particular material. Uses can be banks, courthouses, federal facility, guard stations, anything with a high value asset, which can be occupants or people or something in storage, you know, like a diamond exchange or a Federal Reserve Bank, that sort of thing. Seismic durability. Here we have a diagram. The contour colors show intensity of seismic activity. So you can see there's large areas of the US that are impacted by seismic zones, and the little dots, the red and the black, are the density of population. So you can see that there are many places in the US that have a high density of population that are also high seismic risk. And here's a quick example. On the left, you have CMU. On the right, you have brick. 2,500 PSI for CMU, which is a little bit higher than the minimum, and 4,000 for the brick, which is easily accomplished. The capacity of the CMU wall is 364 kips of shear, whereas the capacity occupying the same volume of the wall is 26% higher, 461 kips. Now, if your demand isn't quite that high, you might even think about reducing the thickness of the wall. So if you go to a 6-inch clay material, you'll get 93% of the capacity of the 8-inch block material, but you have a 26% thinner wall. So you have more usable space. Here's an example of an essential facility fire station made out of reinforced masonry. Talk about ballistic durability. People are starting to be interested in knowing what the capacity of the walls are to resist ballistic attack. There's 4 major US criteria for ballistic testing. These were all conglomerated into one user-specified testing protocol by one particular manufacturer. Here's some of the weapons that were used. Here's an example of the setup, firing through a protective polycarbonate barrier at the walls. 18 different protocols that were tested, ranging from 22 long rifle up to a 50 gauge sniper rifle, including armor piercing rounds, and they all passed for the 8-inch solid grouted wall of a particularly modified brick unit called armor brick. And here's an example of a potential use. We have a detail used for the vestibule of a school, which was modified at some point because you can see the deltas and the clouds, where they added a ballistic resistant fiberglass panel, interior CMU covered by an exterior masonry veneer. So here's the assembly that was used for this particular facility. As fiberglass panel, brick veneer, and brick ties. That could all be replaced with a single wide of structural ballistic rated brick to provide the same protection level. And then the interior wall can be produced with light gauge furring for the insulation, and then sheetrock. The assembly on the right is a much less expensive than the assembly on the left, because the assembly on the left uses the fiberglass panels that can range anywhere from $10 to $47 a square foot. And you get extra interior space. And if you use smaller studs and reduce the airspace between the insulation and the exterior width of the brick, you can even have more interior space. So where can these be used? Guard stations, school corridors, courthouses, again, facilities with high value assets, hardened vestibules like this case that we just reviewed. Some of the assemblies that can be used with hollow reinforced clay masonry are single wide reinforcing walls used as bearing walls, shear walls, foundation walls, retaining walls or site walls. Structural curtain wall might be a new concept for you in structural veneers. You can do multi-width walls with insulated space in between the Ys for high loads on the left. Both walls are fully grouted and reinforced with almost continuous insulation in the middle. or a highly insulated wall on the right where the unreinforced cells are filled with insulation. So you can get a fairly high R value that way. And here is the pseudo modular wall using the 16-inch units that are overlapped 1/4 or 3/4, but the slot in the middle makes it looks like a typical running bond application for modular brick. That's what the units look like. They can also be precast, or not precast, but prefabricated panels, like precast, reinforced with lifting eyes and hardware on the backside like precast, and lifted and flown into place on the exterior of the building. Structural curtain walls are self-supporting exterior enclosures. They're designed to resist all the environmental loads. They are not part of the primary force resisting system of the primary structure. They're just tied back at the floors for perpendicular to plane stability, so they don't get sucked off the building by wind loads and so forth. And they're typically supported at the foundation level. So here is the first application of a masonry curtain wall, which was the Chicago office of the Home Insurance Company in Chicago. It was the first qualified steel skyscraper because the steel framing carried all of the gravity loads. The masonry didn't have to carry the gravity loads of the building, so the windows could be larger because the masonry could occupy less space. And here's an example of the condition where it's a more modern reinforced exterior masonry wall tied back at the floors. Here's an example of where it's used. This particular adjacent property did not want scaffolding on their property, so the wall was built from the inside out. Here's a quick diagram of how the building went together. So the interior bearing walls and the exterior curtain wall were built one floor at a time. Then the concrete planks were added, used as the next framing level, and so forth and so on to complete this building. So the exterior walls and the interior bearing walls went in first, then the floors, then the next level up, and so on. When those were finished, the insulation was added, then interior partition framing, which is like the 22 or 25 gauge studs, rather than the 16 or 18 gauge studs that would be required for a typical brick veneer. But in this case, you couldn't put a brick veneer on because you had no access on the adjacent property. Here's an example of an apartment building. The savings in scaffolding alone was roughly almost $200,000 in the 1990s. It's 1996, I believe, equivalent of $335,000 today's dollars. Cut 2 months out of the schedule, no shelf angles, no perimeter beams supporting any of the exterior wall. Total savings on the building was $850,000, which was about twice the cost of the masonry. And in today's dollars, that would be almost $1.5 million savings. Here's an example, another example of a curtain wall, self-supporting, resisting all the wind loads. Get the same appearance on the inside as the outside due to the single wide construction. Structural veneers are similar, all the same sort of aspects. It's self-supporting. The big difference here is it's typically supported at each level, and this is used in areas that have to accommodate large story drift, generally driven by seismic design. So you have individual walls supported each floor, tied back at the top of each floor. And that way the horizontal story drift can be accommodated in the horizontal joint, but this material takes care of all the environmental loads, so forth. Here's an example of a facility in Salt Lake City. These exterior piers were originally designed as a brick veneer over steel stud framing. It was value engineered into a system here of 2 different bricks. We basically have this one with 2 slots on one face, 1 slot on the other face. This one with 1 slot on one face, no slots on the other face. So to compare, 2 courses of this assembly requires 10 units. 2 courses of this assembly requires 17 units, plus the brick ties, plus the higher gauge wall framing behind to resist the wind load. So what they enjoy a significant savings by going to the system on the right. Here's some quick shots of some buildings. Here's a commercial office building that projects out over the sidewalk to provide more rentable and leasable space on the upper floors than the lower floors. You've got specialty shapes on these reinforced, all of these walls here that cantilever out are all reinforced masonry walls. And the soffit area is basically a series of reinforced hollow clay masonry lintels, so there's no steel lintels visible anywhere. Here's a 17-story hotel that was built in the mid-1970s, still doing just fine. Here's a Jewish synagogue that's got, if you stand in one space and spin around 360 degrees, there's 13 different reinforced masonry beams in this room. And the masonry beams are supporting approximately 50% of the roof. This masonry beam spans across and is supported by this masonry beam. Here's another masonry beam. Here's a reinforced masonry arch, another masonry beam there. This is a water treatment facility. This exterior wall is 10-inch, no pilasters, 40 feet high. This wall is also 10-inch wall. These shorter walls on the sides are 8-inch reinforced masonry. Here's the finished product. This is also designed in the high seismic zone. You want to have culinary water after an event. This is a very durable building to house all of this water treatment facility. Here's an example of a school using multiple colors. Here's a reinforced masonry pier, cantilevered beam, reinforced masonry beam over the entry. And one of the last examples is a project for a university stadium. This is the conceptual early drawings. They wanted to have masonry soffits and a masonry arch in the front. So they chose to use reinforced masonry for those materials. These beams basically support the gravity load due to the shallow arch action of that entry. Here's a rendering of what they hoped it would look like at the end of the day. And here's a photograph of the finished product. All of the brick in this view is reinforced hollow clay masonry. And final wrap up, durable structures aid personal resiliency and can be built with hollow reinforced clay masonry. Personal resiliency benefits all other resiliency issues, neighborhood, community, etc. And a real brief blurb about the illusion of certainty. So the building codes provide minimum standards based on collapse prevention. So after an event, hopefully, if it falls within the design standard, you'll have a building that's intact, but maybe not usable, but it hasn't fallen over. Certain essential facilities move to a different criteria called performance design, where you may need to have immediate occupancy, like fire stations, hospitals, police stations, and that sort of thing, which has to be much more durable buildings. In reality, no matter what you design for, there can be an event that exceeds those design criteria. You know, if you designed for a 100-year flood, you could have a 400-year flood. If you designed for a certain earthquake magnitude of acceleration, you could have an earthquake that exceeds that. So the key is to make durable facilities with robust materials that have some capacity beyond the minimum design strength. Should be designed for redundancy and ductility. Those are what you want to have. And reinforced hollow clay masonry can do those things. It's strong, it's tough, and it's proven by numerous facilities having been built with this material. It can resist wind, debris, fire, water, earthquakes, bombs, and ballistics. And again, durable facilities enhance resiliency for individuals and communities. Thank you for your attention. Are there any questions?
All right, so if anyone has any questions, please feel free to put them in the Q&A or chat, and we would be happy to field them to Stephen and his team.
And if you have any questions, like tomorrow you wake up, you say, hey, I should ask this or whatever, you can always contact any one of us three and we can respond to you directly.
Any takers? I feel like we might need some Jeopardy music.
So anyway, it's a pleasure to be with you today. I hope you have a good design conference. appreciate Hillary hosting and introducing us, and also want to thank Shannon Perry and Don Strange, who are in the wings, able to answer any questions you might have.
Awesome. And as Stephen said, I will connect everyone via email following today's presentation. And if you've made it this far, we will submit you for AIA credit. And more information on the Monterey Design Conference is available on the AIA California website. Oh, we do have a question in here. The cost relative to CMU.
It's a good question. Shannon, do you want to answer that?
Well, that is a very general question because we are not actually always looking at unit prices and comparing them. If you just compare a unit price, the reinforced hollow clay brick is going to be more expensive most all of the time than a concrete block, as it well should be. What we want to do is look at entire wall systems and see what other things they're going to replace, and also see what the labor costs are in those wall systems. So if you're comparing it to a block and a brick multi-width wall system, going to a single width and narrowing your foundations and decreasing your trades and reducing your schedule, there are a lot of costs savings that you could see outside of just the masonry trades, outside of what the brick distributor or manufacturer is going to be able to quantify. If you're looking at a single width comparison where your block is an architectural block with texture or burnished block, then the costs become pretty close to equal. And then you also want to look at your life cycle costs. So how long is that building meant to last? If you're looking at a concrete product, you're probably going to have to treat that with sealer. And that's going to be a maintenance thing that you're going to need to do, on a regular basis for the life of the building. And you're also going to have more movement joints, fewer movement joints with a clay unit. And then you generally don't need the maintenance of having to apply a sealer to it. That depends on your project location and your climate. Generally, we don't need that. And the color is steadfast for the life of the product. And beyond the life of the building, actually can be reused.
So in addition to that, what Shannon was saying is you need to look at the total long-term cost. There's a school district in central Utah that did a study of their CMU buildings and their reinforced hollow clay masonry buildings. And they found that the hollow clay masonry buildings required roughly only 20% of the maintenance cost over time compared to CMU. So they have chosen to only build using hollow clay masonry because of the long-term cost savings, even though the initial construction cost is somewhat higher than it would be for CMU.
Don, did you have anything to add?
Yeah, I would just kind of mirror what they said. The initial cost of just the wall itself, depending on which system you go with, block and brick or brick and steel studs or other things, can be initially maybe a 20 to 25% savings in dollars, but it can also accelerate the building schedule by 50%. So it's a quicker thing. But then beyond that, there's the cost of the building, and we can pull a lot of other materials out of it. And there is the cost of ownership, which is that life cycle thing. So it's significant savings and quantifiable savings that we look at daily on project specific opportunities that we have. Where is it built? How is it being used? How long do you want to own it? Is it temporary or longer? Most buildings are 100-year buildings anymore. And of course, when you're looking at it that way, it's significant savings.
Wonderful. Thank you again, Pacific Coast Building Products, Interstate Brick, Stephen, Shannon, Don, Ed, Don Sackett. We appreciate your guys' presentation today. Again, the recording will be shared with everyone, and let us know if you have any questions. Thank you.
Thank you.
Thank you again.
Great job.